So now we're going to go over what the graphs of the sine and cosine functions look like. We know how to evaluate them. However, we want to see if we were to turn this into a function, y equals sine of x, for those different x values, which is our input, we want to see what does that graph look like. But we know it's very circular in motion, okay? So the values of our sine and cosine function are always going to repeat themselves because it's all about where that angle lands on the unit circle. So if you consider sine of 0 degrees, it's again a little easier to work in degrees to start with. That's the same thing as going 1 revolution around. So it's also equal to sine of 0 degrees plus 1 revolution, because it lands you in exactly the same spot. Or if you go around 2 revolutions, which would be 2 times 360. And then you can keep doing that, because regardless, you start here, going once around lands you in the same spot. Going twice around lands you in the same spot. Going 3 times around still lands you right back here, and you only ever look at the y coordinate to get the output. So it's exactly the same. So true or similar story for the cosine function. In general, if I have sine of theta, it's going to be exactly the same thing as if I take that angle and I add any multiple of 360 degrees. But again, I said we like this in radians. That's going to be our main input. So the way we write this is 360 degrees is equivalent to 2 pi. And then n is the number of revolutions. So this would be plus 2 pi, plus 2 times 2 pi. Next one would be 3 times 2 pi. So in general, we can add any multiple of 2 pi, and it will be 1 revolution around and get me in the same spot. And likewise for the cosine function, same thing. You can add any multiple of 2 pi. So this just tells you it is n revolutions from that same position. You still land in the same spot on the unit circle. So this n is just an integer. It can be positive, it can be negative. Negative means you just trace it in the opposite direction, no problem. The shorthand for this, because we are going to use this a lot, is we say n is an element of the integers, which is denoted with a z, okay? When you have functions that do this, where you can add some constant or a multiple of that constant and still get the same result, they're called periodic. So functions with this property are called periodic, okay? So sine, cosine, periodic, which in turn makes all of our other trig functions also periodic. The period itself is the shortest length over which the function repeats. So for us, that's going to be 1 revolution around, so our period is going to be 2 pi. For this particular trig function. So now at this point, when we talk about the sine and cosine functions, your input is going to be in radians. We are not going to input degrees to graph it on an XY plane. So we're going to start with what the graph of y equals sine of x looks like, and then we'll do y equals cosine of x. What I'm going to do is I'm really going to focus on the quadrantal angles, because plotting those other intermittent values, you could plot 1/2, that's not terrible, but plotting root 2 over 2 and root 3 over 2, not so easy. So instead I'm going to focus on the quadrants. My first important angle is 0 degrees. Next one is 90, which is pi over 2. Then we've got 180, which is pi. Then 270, which is 3 pi over 2. And then we come back to where we start at 2 pi. Sine of 0 is 0. Sine of pi over 2 is 1. Sine of pi is 0. 3 pi over 2 is the negative y-axis, so it's -1, and then we end at 0. So remember, our sine and cosines are always trapped between -1 and 1, so I'm never going to go past those values. And I ultimately have 5 main quadrantal angles. The starting and ending happen to end, they start in the same spot, but they're both important for plotting. So I'm going to plot all of these values. We've got 0, we've got pi, 2 pi, and then these are those 90-degree angles, pi over 2 and 3 pi over 2. So starting out, sine of 0 is 0, sine of pi over 2 is 1, sine of pi is 0, 3 pi over 2 is -1, and then at 2 pi gives us 0. These angles from 0 to pi are the top half of the unit circle, so your sine function is positive. If you think about 0 to pi over 2, that's quadrant 1. So what happens is your y value starts at 0 and gets bigger and bigger and bigger. Then from 90 to 180, the y value gets smaller and smaller and smaller and goes to 0. So our graph kind of follows that circular motion where it increases, 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 and then comes back down till it lands at 0. From pi over 2 to 2 pi, that would be the bottom half of the unit circle. So your y coordinates are negative there. So in this case, I increase out to -1 and then come right back, okay? And that gives me 1 full revolution around the unit circle. So I land exactly where I start. So the period of y equals sine of x is 2 pi. That's when I complete 1 full revolution. But now at this point, I would just go ahead and I would continue the same graph because I go around the unit circle in the same way. And if I go in the opposite direction, same thing, it's exactly the same graph because I go around the unit circle the same way. So the graph is just going to repeat itself. Over the interval 2 pi to 4 pi, which is length 2 pi. That's my next revolution. After that would be from 4 pi to 6 pi. And then you could keep going, but then you have the negative cases as well. So you also have from -2 pi to 0. That would be 1 backwards revolution. The interval prior to that would be -4 pi to -2 pi. And then you keep that process going, okay? So that ultimately gives us a full picture of our sine graph. It's trapped between 1 and -1. It will repeat itself every 2 pi. So our graph of the sine function starts at 0. It goes up to +1, down to -1, and then comes right back to 0. Then that just gets copy and pasted over each interval of 2 pi. We go up to +1, down to -1, and then back to 0. Same thing on this interval. We go up to +1, down to -1, back to 0. Up to positive, down to negative, back to 0. And then that graph just keeps going onward and repeats that process. So you'll often hear these called sinusoidal waves or cosine waves because it's just going to do the same thing over and over and over again. So these are extremely applicable because you can think of a lot of frequencies that have the same kind of pattern. You look at heart rates and all of that kind of stuff. It's just more complicated where it has dampening added to it. But these are really essential to model a lot of realistic stuff. So if we think about all of the properties of the sine function, your domain is you're inputting an angle, because this is the graph of y equals sine of x. You can input whatever angle you want. So your domain is all real numbers from negative infinity to positive infinity. Your range, however, is the y values. That will only take on -1 to 1. The max value you're ever going to have your graph equal is 1. And your min value is -1. Your period, in this case, is going to be 2 pi, because that's the length that repeats itself, okay? So if you know these basic functions and you know what sine and cosine are for these quadrantal angles, when we start making the inside more complicated and moving it left and right, stretching, shrinking, all of that kind of stuff, it really just boils down to all of those key points happen on the quadrants. So when your inside is a quadrantal angle. So if you can figure out what x value makes the inside equal 0, makes the inside equal pi over 2, pi, 3 pi over 2, and 2 pi, you can plot your full graph and you're good. And you can find your period that way. So we will talk about that in the near future. But let's start now with going over what the basic graph of y equals cosine of x looks like. So again, I want to go through the quadrant angles and then we'll see how that ends up repeating itself. But 0, pi over 2, pi, 3 pi over 2, and 2 pi are the quadrant angles. Cosine of 0 is 1, cosine of pi over 2 is 0, pi is -1, 3 pi over 2 is 0, and 2 pi lands me back at 1. So again, same thing, you go through a full revolution around the unit circle from 0 to 2 pi. And then we hit all of those main angles in between them. The other thing to notice, this point is exactly in the middle of these two. This one is halfway in between these two. And this one is halfway in between these two. So when we have to go to label our graphs in the future, that's one way we can go about it. But for our cosine function, the starting shape is going to look a little bit different because we start at +1, then 0, then -1, 0, and +1. And again, we go really fluid through this, and it ends up kind of looking like a V, more like a valley, okay? So this function, cosine of x, is also 2 pi periodic. Okay. So then I can copy and paste this over the same intervals because again, it just repeats around that unit circle. And although these sine and cosine functions look different right now, once we go ahead and plot a couple periods, they really become the same thing. So again, between 0 to 2 pi, I have the same shape. So we'll do intervals of length 2 pi. Our main function starts here at 1, and then we'll come back to 1. And then it goes down and back up. Then we copy and paste, goes down, back up, goes down, back up. And then same thing, goes down, back up. So ultimately your graphs look pretty identical, they're just shifted. So you still end up with this wave shape, okay? And that makes sense because again, these are complementary functions. The only difference is that starting point. It's just a shifted version of the other. So here, really, all of the same properties are going to hold. Your domain is any angle you want. Your range is just the numbers -1 to 1. Your max value is +1. Your minimum value is -1. And your period is still 2 pi. Okay. So what we're gonna do now is we're gonna go ahead and apply all of these different transformations. They do have different names because these are periodic functions and they're important for us. So we're gonna go into detail about each one and how it affects the graph, and then utilize that to get the picture of the graph. So the first concept we're gonna start with is called the amplitude. So remember, if you take a constant out front of your function, that's going to be a vertical stretch or shrink, just depending on the value of c. So to think about that, we're going to compare the graphs of y equals cosine of x, y equals 1/3 cosine of x, and y equals 3x on the interval from 0 to 2 pi. Okay. So if you think about what this 3 does, it takes the cosine function and it takes the output and triples it. So what ultimately is going to happen, instead of being stuck between 1 and -1, your y value can go up to 3. Again, we will show that in a minute. My inside isn't changing at all, so all of my angles I don't have to worry about. We're still going to be concerned with the quadrants. So we'll start out with y equals cosine of x. Cosine of 0 is 1. Pi over 2 is 0. Pi is -1. 3 pi over 2 is 0. And then 2 pi lands me at 1. So this gives me my base function that I'm working with. And it has that wave shape. Now if I try to do 1/3 cosine of x, when I plug in 0, that would be 1/3 times cosine of 0, which is 1. So your y value is going to get cut to 1/3. When I plug in pi over 2, cosine of pi over 2 is 0. So timesing it by 1/3 does nothing. This point is exactly the same. If I replace this by pi, let's see if I can use a color that you can see a little better. That would be -1. So timesing it by 1/3 gives you -1/3, which is around here. Evaluating this at 3 pi over 2 gives you 0. So timesing it by 1/3 does nothing. And then back to 2 pi, it's the same thing as 0. Its output will be 1/3. So this shrinks that graph and makes it a less sharp curve. Okay. Graphing 3 cosine of x, all that's going to do is take these values that were y and multiply it by 3. So if I plug in 0, that would be cosine of 0, which is 1. Timesing it by 3 puts it all the way up here. If I plug in pi over 2, well, this color is not the best option, so let's try a different one. So it'll at least color over top. When I plug in pi over 2, you still get 0. Plug in pi, you'll get -3. 3 pi over 2 results in 0. And 2 pi comes back up to 1. So our graph looks like this. So it's taken the original graph and it's just stretched it vertically. Okay? Where the 1/3 shrunk it vertically. Okay? So this is called that amplitude of our function. Doesn't matter if I switch this to be sine instead, it is still the amplitude. So functions of the form y equals a sine of bx and y equals a cosine of bx This value out front is going to deal with your amplitude. But the amplitude itself is just going to be a positive number. So I don't care whether it's positive or negative. That negative is going to correspond to a reflection. But it is just the vertical stretch or compression. So in that last example, y equals 3 cosine of x, the amplitude is positive 3. When you have just cosine of x, that's a 1 out front, so your amplitude is 1. 1/3 cosine of x gives you an amplitude of 1/3. Again, it wouldn't matter if I put a minus sign here, your amplitude is still positive 3. It is just a positive number, okay? So that's our first transformation that we can do. That's affecting the range. So no longer is this graph stuck between 1 and -1. It's trapped between 3 and -3. This graph is now trapped between 1/3 and -1/3. This number on the inside affects the x, and it's still a stretch or shrink, but in the x direction. And it does the opposite of what you would think. So when it was 3, it made sense. It made the graph much bigger. When it was 1/3, it made the graph much smaller. But if I put that on the inside, it's going to do the opposite. It doesn't make it bigger in the x direction. It's going to make it smaller, okay? So this is going to impact our period. Y equals cosine of x and y equals sine of x are 2 pi periodic, and they go 1 revolution around the unit circle when the inside is 0 and when the inside is 2 pi. So if I now multiply the inside by a constant, it's going to affect how quickly I move around the unit circle. So I'm going to complete 1 period when the inside equals 0. That's when my period will start. And it will finish when the inside equals 2 pi, which is that last important quadrantal angle. So in this case, it completes the period still starting at 0, but ending when x is 2 pi over b. So I really don't like memorizing formulas with this stuff. Okay? So yes, you can find your period by taking 2 pi and dividing it by this constant in here. However, I really don't like that method. Same thing, we'll talk about what happens if I then add something in here. What does that plus c do on the inside? There are formulas for it, but I personally don't think it's beneficial to just memorize a formula. Instead, I know this is going to impact it horizontally. It's going to stretch or shrink it. But again, I'm going to know when my inside equals 0, that's when I'm starting the formation of my unit circle. And when the inside equals 2 pi, that's when I've gone through a full picture of my sine function and my sine graph, okay? So we're gonna try another example of this. We're gonna just start with some simple numbers on the inside. Graph y equals sine of x, sine of 2x, and sine of 1/2 x, okay? So I'm gonna add in some pictures here because again, I already know the answer to what this has to go out to. I'm just gonna count by pi's. So we'll go out to 4 pi. So my graph of the sine function is trapped between 1 and -1. I have a 1 in front of each of these, so it's not impacting that at all. My normal graph of the sine function starts at 0 and then ends at 2 pi, and it goes, and at pi 0, so it goes through one full picture of my sine function. So this is my starting graph, okay? We're gonna go ahead and graph sine of 2x first and see how that impacts the period. Again, this impacts x. You would think it multiplies x by 2, but it's always going to do the opposite. So instead of being from 0 to 2 pi, it's going to be half of that. So y equals sine of 2x completes one period. From when the inside equals 0 to when the inside equals 2 pi. So solving for x, you divide by 2. So it completes one full revolution from 0 to pi. So from 0 to pi, I go through a full sine wave. So my graph got smushed in this direction, okay? So this one is my graph of y equals sine of 2x. So now when I plug in x equals pi, I get sine of 2 pi. That ends my unit circle. So it's smaller angles that land me on the quadrants instead. If I look at y equals sine of 1/2 x, this completes one period. From when the inside equals 0 to when the inside closes out that unit circle and ends at 2 pi. So solving for x, you can just times by 2, which ends up giving you 4 pi. So for this function, it's going to take from 0 to 4 pi to go through a full revolution. And so in that case, you can go ahead, we'll talk about finding the key values after this, but it's got to go up and then it's got to come back down. You can think if you plug in 2 pi, 1/2 times 2 gives you 1. So that gives you 0 here. So your graph ends up looking like this. Okay. So that number on the inside is affecting your period. Again, your number in front here is 1, so it's 2 pi over 1. Your period is 2 pi. Take 2 pi and divide it by 2, your period is pi. So over an interval of length pi, you go through a full revolution. 2 pi divided by 1/2 is 4 pi. So over an interval of length 4 pi, you go through one revolution, okay? So let's try an example where we'll combine a bunch of different things here and find key characteristics. We're gonna graph y equals -3 sine of 1/4 x over a single period. So just to show you those key features, because you're gonna be asked them if you wanna find the amplitude. Again, I don't care about that minus sign. The amplitude is 3. That tells me my graph is going to be tracked between -3 and +3. It's just a number it stretches by. So our period in this case is going to start when the inside equals 0. And it finishes when the inside equals 2 pi. So solving for x, you multiply by 4. Your period still starts at 0, and it will finish at 8 pi. So we can go ahead and graph the function over 0 to 8 pi, and that will make one full sine curve. This 3 bumps it, so it's tracked between -3 and +3. And since this number is negative, remember that's going to be a y-axis reflection. So if you think about your graph of y equals x squared, it's shaped like this. Negative x squared again goes downwards. So I'm going to take my graph that I draw over that interval from 0 to 8 pi, and then I just flip it to go the opposite way, okay? So since our value of a is negative, we need to reflect the graph over the x-axis. Okay. So I'm going to go ahead and I'm going to start drawing a little picture. We're trapped between 3 and -3 now because of that amplitude. And I know that I'm going to start when x is 0 and end at 8 pi. So my ending value is over here. Okay. So I can definitely go ahead and plot everything first, but then I want to go back and label my points a little better. So I know there's one halfway in between, and then there are 3 other key values I have to find. So again, just to go back up here to show you, we have 5 main quadrantal angles. So there are 5 key components we need to find. 2 of them you find already just by setting the inside equal to 0 and 2 pi. So if I didn't have that minus sign, I would go ahead and graph my function as normal. So sine starts at 0, then it hits that maximum, back to 0, the minimum, and back to 0. And then I'm going to graph this as a dotted because, again, this isn't my final graph. Instead, this would be if the thing was positive. So this would be the graph of 3 sine of 1/4 x. But because it's negative, it's going to flip all of those points. Well, flipping anything at 0 doesn't do anything. This point is going to flip down and become -3. My next key value still is 0. This one flips up to +3. And then I land back at 0. So this is what my graph actually looks like over one period. Okay. Now what I want to do is I want to more thoroughly label all of these key pieces. Okay. These happen at the quadrantal angles. That's when you get a key peak of either 0 or the biggest or smallest your graph can be. So we're going to find those other important points. So we're going to find when the inside equals a quadrantal angle. So I'm going to set the inside equal to 0. The inside equal to pi/2. The inside equal to pi. Then 3 pi/2. And then finally 2 pi. And again, realistically, you can just go ahead and do this to start with. And then you know when your period starts and your period ends. It's the first and last key value. So in each of these cases, if I go ahead and solve for x, I just times by 4. So my first key value is 0, which is that. Pi/2 times 4 gives you 2 pi. So the next key value happens at 2 pi. Timesing by 4 gives you 4 pi as your next key number. Timesing by 4 would give you 12 pi/2, which is 6 pi. So that's the next key number. And then again, timesing by 4 gives you 8 pi, which is that final key value. Okay. And again, realistically, you can also find these because they're going to happen halfway in between. You start at 0, end at 8 pi. Halfway in between is 4 pi. Halfway in between 0 and 4 pi is 2 pi. and then halfway in between these two is 6 pi. That can get a little bit messy if you don't have as nice of numbers to work with, especially if like this is going to be like pi over 6 or 7 pi over 6. Finding that halfway point's a little bit more difficult. So again, just set your inside equal to those quadrantal angles. Okay. Before we talk about what happens if I then add a number inside here, we're going to go ahead and try an example where we need to find the equation for the graph. Okay. So I need to find two things. I need to find what is my amplitude. I need to determine if there's been any flips or anything like that. And I need to go ahead and find what is my period. And again, you'll be given directions, but your equation for the graph could be a lot of things. In this case, we're going to keep it simple. Find the equation for the graph where your y is equal to a sine of bx, or your y is equal to a cosine of bx. We're not going to worry about any other transformations. So I have not moved this left and right just yet. So starting out, if I look at what my graph is trapped between, my biggest values, +2 and -2 is my smallest. So my amplitude is definitely 2. I don't know whether it's +2 or negative out front. I need to see if there have been any reflections. And again, I haven't moved this, so my period is going to start at 0. I want to figure out when do I go through a full sine or cosine curve. And so in this case, if I trace this, I start at -2 and I keep going, keep going, keep going until I end back in the same spot. So my period actually ends at 4. And then you can see that over here at -4, same thing, it cuts my graph. So this is my shape, which isn't any of my trig functions in the normal form. But if I were to go ahead and flip this around, that would be the cosine function over the interval from 0 to 4. But I've just reflected it, okay? So this is a cosine function. Reflected across the x-axis. So that tells me my value of A is going to be -2 to get that reflection, right? I need to figure out what my value of B is then, and that's where I'm going to go ahead and use the period. My period begins when my inside 0, and it ends when my inside is going to be 2 pi. So based on the graph though, this period begins when x is equal to 0, and the period ends when I plug in 4, okay? So we're going to utilize this to figure out B, okay? So there's a couple different ways you can do this. You can go ahead and set this side equal to 2 pi, and that's when it ends. So bx equals 2 pi is the end of your period. You know this happens when x is 4. So we can utilize that to solve for b. So dividing both sides by 4 gives you b equals 2 pi over 4, which is pi over 2, okay? Or if you want to go back up here and use your formula, your period is 2 pi over b. So 2 pi over b is going to equal 4 because that's our period length. And then again, just rearranging this would give you the same thing. You would get pi over 2 is your value of b. So our actual equation for this graph, our value of A is -2. we are dealing with a cosine function, and we have pi over 2 as our value of b on the inside. So this is the equation of our graph, okay? All right, so the very last thing we're going to do is generalize this as much as we can. So not only are we going to have the stretches and shrinks horizontally and vertically, we can also go ahead and do horizontal shifts and vertical shifts. These ones are not bad, those just move it up and down, but this moves it left and right. So it does make it a little bit more complicated, okay? But I'm still gonna utilize the same idea. I want to get one period for my sine or cosine function, either one. Your period's going to start when the inside equals 0, and it's going to end when the inside equals 2 pi. So my period begins when whatever is in the inside equals 0 and ends whenever the inside is 2 pi, okay? So you're concerned for the x values this happens for. So if I solve for x, I go ahead and subtract c, and then I go ahead and divide by b. Okay. Likewise here, I go ahead and subtract c, and then I divide by b. So I'm going to divide both things by b. Okay. So you can consider this first one 0 plus negative c over b. And then it ends at 2 pi over b minus c over b. So this number here is being subtracted for each of them. This is called our phase shift. And then this here is still the period. Okay. So ultimately your phase shift is just a horizontal shift, but what you would have to do is you'd have to factor out that value of b to see it. Okay. So it always moves the opposite of what you want. If it was plus 3 attached to the x, remember that's going to move it to the left 3. So as a quick example, if you think of y equals the square root of x minus 1, you would think that would move it to the left 1, but it actually moves it to the right 1 because your x values have to be bigger than 1 here, okay? So the phase shift is just a horizontal shift. And then that plus d or minus d, whatever it is a vertical shift. We will take care of that at the very end and not bother with it until then. So let's go ahead and we're gonna graph y equals 4 cosine of 2x minus pi over 1 period. So we'll identify all the different things again within here. Your amplitude in this case is 4, so we'll be tracked between -4 and +4. Your graph is going to start, or your period is going to begin when this inside is equal to 0. And the period is going to end when the inside equals 2 pi. So this will tell us what two numbers the full graph of the cosine function covers. So solving for x, we go ahead and add pi, then divide by 2. So our graph is going to start at pi over 2. So instead of starting here at 0, I'm going to go ahead and push that forward, and it's going to start at pi over 2. So it's moved it to the right. So this value is my phase shift. Then to figure out what my ending value is, we again solve for x here. So if I add pi, that gives me 3 pi. Divide by 2 gives me 3 pi over 2. So the interval for one period is going to start at pi over 2 and end at 3 pi over 2. Okay? So I will graph everything between these two values. If you need to know the length of the period, well, again, it's 2 pi divided by this number, but it's also just the length of this interval. So it's the ending value minus the initial value. 3 pi over 2 minus pi over 2 is 2 pi over 2, which is pi. Or again, the period is 2 pi over b. The value of b in this case is 2. So 2 pi over 2 gives you a length of pi, okay? So our phase shift is pi over 2. Like I said, typically you like a direction associated to this. It just depends on the book that we use at the time. But you started at 0, you've moved it to pi over 2 as your starting point. So it's pi over 2 to the right. Okay. So we can go ahead and we can at least get a start for this graph. But again, I want to find those key values overall. We are now trapped between 4 and negative 4. My graph is going to start at pi over 2, and it's going to end at 3 pi over 2. I'm dealing with a cosine function, so I start at my peak, then I hit 0, then I hit my minimum. Come back to 0, and then go up to my peak again to get my valley shape. So this would be the graph of 4 cosine of 2x minus pi. I don't have to flip anything. But again, I want to know what these key values are here. There are 3 key numbers for those key points. So you could find it by finding what is halfway in between pi over 2 and 3 pi over 2. And then you would have to find those by finding the halfway point of each of these intervals. Or again, just set the inside 2x minus pi equal to 0, equal to the next quadrant angle, which is pi over 2, then pi, then 3 pi over 2, and then finally 2 pi. I'm not going to bother with these first two because that's what we've already done. This was to find what interval we graph it over. So 3 pi over 2 to 3 pi over 2. Okay. Solving for this first one, I need to go ahead and add pi to both sides. So pi over 2 plus pi gives me 3 pi over 2. Dividing by 2 gives me my key value of x being 3 pi over 4. So this key point here is corresponding to x being 3 pi over 4. This next point, we add pi, so that gives you 2 pi dividing by 2 results in pi. So my next key value happens when x is equal to pi. Then the last one, adding pi to 3 pi over 2 gives you 5 pi over 2. Dividing by 2 gives you 5 pi over 4. So this key value happens when you plug in x equals 5 pi over 4. Okay. So that is the graph of this particular cosine function. So I'm going to do one more, which is going to have everything. It's going to have a phase shift. It's going to have an amplitude. It's going to have a reflection. It's going to alter the period, and it's going to have a vertical shift. So we are going to graph -2 sine of pi x plus pi plus 1 over 1 period. Okay. And again, I'm going to ignore this one for right now. I'm going to focus on doing this, and then I'll go ahead and add that plus 1 in the end. My amplitude in this case is 2. And then because my A is negative, we're going to need to reflect over the x-axis. But I'll do those reflections after I graph it once. I want to figure out what I need to start my period at and what I need to end my period at. So my period begins when the inside is equal to 0, and my graph will end when the inside equals 2 pi. Okay. So this will tell me what the interval is for one period. And then to actually get that period length, again, remember, we can subtract the 2, but it's 2 pi over b, which in this case, the value of b is pi. So it's 2 pi over pi. My period will have length 2. Okay. So again, to figure out what specific numbers I graph over, we're going to go ahead and solve these two equations. So I made a slight typo. This should be pi x plus pi because that's the inside here. But going through and solving for this, we subtract pi. So that gives us pi x equals negative pi. Dividing by pi gives us negative 1. Subtracting pi over here gives you 1 pi. Dividing by pi gives us positive 1. Okay. So my period, I'm going to graph this over. It's going to start at negative 1 and end at positive 1. So again, the length of that is an interval of length 2. Our phase shift, again, depends on the book exactly how you write this. In some books, it'll say your phase shift is just negative 1. If it wants the direction, we are going to move this 1 to the left. Your original value is 0. It's now starting at negative 1, so it's moving to the left. Okay. So I have everything I need to graph this expression, ignoring that transformation. Then we'll go ahead and take care of that reflection, and then we'll go ahead and take care of the shift, okay? So starting out, we're gonna graph y equals -2 sine of pi x plus pi first, okay? So I know I need to graph this from -1 to +1. My amplitude is 2, so I'm trapped between that. This one isn't so bad to find your key values because, again, these are nice numbers. Your middle point should happen halfway in between. Halfway in between -1 and 1 is 0. And then these two numbers are the other key points. Halfway in between 0 and 1 is a half. So really, without doing any work, these values should be -1/2, 0, and 1/2. But again, if you want to find the important points before you graph first, go for it. You set the inside equal to 0, the inside equal to pi over 2, the inside equal to pi, the inside equal to 3 pi over 2, and finally the inside equal to 2 pi. This results in our starting point, which is -1. This results in our ending point, which is +1. To solve for this number, if I subtract pi, that gives me pi x. That'd be 1/2 minus 1, so it'd be -pi over 2. Dividing by pi gives me -1/2. Exactly what we found. For here, when you subtract pi, that gives you pi x equals 0 or x equals 0. Exactly our middle point. And then here, subtracting pi gives you pi x. 3 pi over 2 minus pi over 2 would be 1 pi over 2. So you end up with x equaling 1/2. Again, the next key number. So I'm going to ignore the minus sign first and graph my normal sine function. It starts at 0, goes up to 1, down to 0, down to my min, and then back up to 0. So this would be the graph if there is no reflection. So we'll go ahead and draw this as a dotted line. So this would be our graph of 2 sine of pi x plus pi. But now I need to reflect it. So this point will go down to -2, this up to +2. And then our graph looks like this. So this would be the graph of -2 sine of pi x plus pi. Okay. So you think we're done, but remember we ignored that vertical shift, but this thankfully is not bad. That takes all of your previous y values and adds 1 to it. So we now can graph our full thing. By shifting up 1. Okay. So I'm going to go ahead and zoom out a little bit so I can still have that graph in here. We were between -2 and +2, but now that I need to shift up 1, I really need to go up to 3. Okay, and then my key values here are 1/2 and 1, -1/2, -1. So my original graph was here, then we were at -2, then at 0, then at 2, then at 1. And again, I'm just going to go sketch this in because it is just the graph without the shift. So this is -2 sine of pi x plus pi. Now I get my full graph by shifting every point up 1. So this was at 0. It now goes up to 1. This was at -2. It goes up to -1. Was at 0, goes up to 1. Was at 2, goes up to 3. And then was at 0, goes up to 1. So let's go ahead and remove all of the circles I just drew. But we have our points. Now we go ahead and connect our dots. Let's get that one back connected. And this is finally our full graph now with that vertical shift. Okay. So if you need to find the range, you can now utilize your picture to do that, but that +1 does impact what it's trapped between. Your new range would be from -1 up to 3. So it moved everything over 1, okay? So we still have to talk about our other 4 types of trig functions. The tangent function is one of its kind of one-offs. It's different on its own. But to graph the sine and to graph the secant and cosecant, we're going to use the sine and cosine functions because remember, it's just the reciprocal. So if we know the graph of this function, we're going to know what the graph of the reciprocal or the cosecant function looks like, okay? So we'll see how to do that soon.